Hi everyone, and welcome to another seminar at Physics Latam. Today we are happy and honored to have Professor Hiraku Nakajima with a talk on quiver varieties. Professor Nakajima is a distinguished professor emeritus at Kyoto University and currently at IPMU at the University of Tokyo. He is renowned for his work on the interplay between geometry and representation theory. He defined quiver varieties and construct integrable representations of affine cat-Moody algebras and quantum toroidal algebras. His interests include Donaldson type invariants and Coulomb branches of supersymmetric gauge theories. He obtained his PhD from the University of Tokyo in 1991. He was a plenary speaker at the 2002 International Congress of Mathematics in Beijing and received the 2003 Cole Prize in Algebra. Other notable awards include Geometry Prize, the Spring Prize from the Mathematical Society of Japan, GSPS Prize, and Japan Academy Prize. We're very happy to have him with us today. If you have any question during the talk, please do not hesitate to raise your hand. And now I'll leave you with Nakajima-san. Please go ahead.
Thank you very much for kind introduction, and thank you very much for invitation to give me a chance to talk about quiver varieties. So quiver varieties, of course, are very, and the topic which I like, but I don't recently speak about them because I slightly shifted my interest. So anyways, I'm very happy to talk about quiver varieties. So these two, I present these two references. One is by Kirov. So this is about the quiver representation and quiver varieties. So published from IMS. And also I recommend Ginsberg's lecture notes on quiver varieties. I mean, of course, the original paper is also the references. Okay, let me start with the definition. So quiver is a finite-oriented graph, and I use, do you see my cursor? Maybe, yeah. Q0 is a set of vertices, and Q1 is a set of oriented edges. So I denote I give the example of the quiver like this. So if H is an oriented arrow, then O of H is outcoming vertices, and IH is incoming vertices, and J in this case. And then I add copy of vertex like this. So this is the so-called framed quiver. So for each vertex, I put a copy. So this is a copy of I, this is a copy of J, and I add the arrow from the original vertex to this new copied vertex. And then I define the double of this framed quiver. So I formally add opposite edges, so like this picture. So this is the quiver which I will play with. Then I take two vector spaces, V and W, graded by Q0. So Q0 is vertices. So it means that V is a direct sum of VI's and W is a direct sum of WI's. And I take V and W to be complex vector space. You can take any algebraically closed field, but I only take the complex vector spaces. And I assume the dimensions are finite. Okay. Then I define the vector space MVW. Was sometimes if V and W are clear from the context, I simply denote by M. So this is the space of all linear maps corresponding to each arrows, right? So each arrow, for each arrow, I first of all, I put a vector space on vertices, WI for here and WJ for here and VI for here and VJ for here. And I consider the all linear maps, space of all linear maps corresponding to arrows. So concretely, so it's a direct sum over all edges in the original edge or the opposite edge, and homomorphism from V of OH to V of IH, and also linear maps between the framed vector spaces Wi and the original vector space Vi. So home of Wi to Vi and home of Vi to Wi. So this is a vector space, finite dimensional vector space. And in fact, this is a cotangent bundle to another vector space, which I denote by N of VW. So in other words, M of VW is a direct sum of another vector space, NVW, and its dual space. So NVW is a half of vectors, half of the space of linear maps corresponding to edges in the original quiver Q1, and also I only take the linear maps in the first component AI. Then remaining component BI and the linear maps in the opposite direction, it gives a dual space to NVW. So this MVW is a symplectic vector space. Okay, so starting from this quiver and I framing and I double the edges, and then I consider the vector spaces of linear maps corresponding to edges. And this is a naturally symplectic vector space. Then on these vector spaces, there are natural group action. So G is a product of general linear groups of VI. So this acts on these spaces NVW and also MVW by conjugation. And there's also action of GW, which is a product of general linear groups of WIs. Again, this acts by conjugation. And these actions, because this is induced from the action of NVW, so this action preserves the symplectic form. And there's also C-star action, MVW on MVW, which scales the cotangent direction. So I decompose M into N plus N star, and I only scale the cotangent direction. So this is a C-star action, but because of this definition, it scales the symplectic form by weight 1. So we have the action preserving the symplectic form, and we have another action which scale the symplectic form. So we use some classical symplectic geometry to define quiver varieties. So it's important to note that the symplectic form behave, how the symplectic form behave under these actions. Okay. Then next, we want to consider the quotient of MVW by the group G. Also, maybe I should, yeah. The notation G. So this is bold face G, and this is bold face G W. So anyway, so we want to consider the quotient space of MVW by G, but in the not in the ordinary quotient space, but we want to consider quotient space in the sense of symplectic geometry. If you just consider the quotient space in naive way, then this is not symplectic. For example, so if MVW is, since MVW is symplectic, this is even dimensional vector space. But if G is, for example, odd dimensional group, then MVW divided by G as dimension of this quotient space is odd, because we formally consider the difference of the dimension. So this is not the correct notion of the quotient space in symplectic geometry. And you can look at a little bit more carefully why symplectic structure cannot be inherited to this quotient space. So take a point M, bracket M in this quotient space. So I use this notation always. So if I take M denote, without bracket, denote the vector element in this vector space. And if I put on we surround in the bracket, it means it's a point in the quotient space. Or in other words, so I consider the orbit through M, denoted by this bracket symbol. Okay, then I consider the quotient space of the tangent space, tangent space of the quotient space. So then, if this quotient is some well-behaved quotient, then the tangent quotient space is also manifold, and its tangent space is the quotient space of tangent space, the original space, divided by the tangent space to the orbit. And so this by MVW is vector space, so this tangent space to MVW is identified MVW itself. And in particular, this numerator is a symplectic vector space. And we divide by some vector subspace. So if you just take quotient of symplectic vector space by subspace, then the quotient is not necessarily the symplectic vector space. This is because, for example, if you have considered a subspace in here, which is perpendicular to the tangent space, to this quotient, to the subspace, then this is a redundant direction. So in some sense, you must remove this redundant space in order to get the symplectic vector space. And this is already considered there's some standard technique in symplectic geometry how to deal with this quotient space. This is the so-called momentum, which I will explain next. Oh, sorry. Before going to the momentum, I illustrate this technique in the simplest example of quiver varieties. So I choose quiver with one vertex with no edge. So this is Q equals. So sometimes people call this is type A1 quiver. So in this case, I just put the framed vector space. This is another copy of vertex, and consider the linear maps between the two vector spaces V and Ws. And I did not linear maps by A and Bs. So then MVW is a direct sum of homomorphic linear maps from W to V and linear maps from V to W. And the action, G in this case is just a general linear group, and the action is conjugation action. So this is by GA and BG inverse. Okay. So we consider the first we take this second component, and we assume this B is injective. Then this quotient space of injective homomorphism, injective linear maps divided by G is an open subset in this quotient space. Then we can consider image of B. So this is a subspace in W. And this is clearly, if under the conjugation action, the image of B is invariant under the group action. And in fact, it's rather easy to check that you can recover B up to conjugation from the image of B because any injective map is conjugate under that. And also this image of B by definition, by the condition that B is injective. So this image of B has dimension equal to dimension of B. So if I focus on the second component and assume that B is injective, the quotient space is Grassmannian manifold of dimension. Grassmannian manifold of subspace of dimensions equal to dimension B, subspace in W. So this is Grassmannian manifold. And also the tangent space of the Grassmannian manifold at the point through orbit through B is, as I said, the quotient of the tangent space of the original space divided by tangent space to the orbit. So in this case, the original space is this second component I choose, and divide by B times space. So this home of VD is a tangent space of this group at the identity element, and you multiply P. Okay, this is a tangent space of it. Then, because of this form, the quotient space is just the space of homomorphism from B to W divided by image. Okay. So if you just take the naive quotient for this open subset, the tangent space is the first summand, which I didn't touch at all, and this component. Then you see that, as I said, this the direct sum is not the symplectic vector space because so the dual space of this vector space is just given by exchanging the target and the domain. So in this case, home space of homomorphism from W divided by image B to B. And the first component is larger. So this is a space of homomorphism from W to B, right? So this is naturally subspace. This space, the dual to this space is naturally in the subspace because it means that you consider the linear maps from W to B, which vanishes at image B. So this is a subspace. And this difference is a redundant direction which I mentioned. Okay. So in order to consider in order to get the correct quotient space in the symplectic geometry, somehow you need to replace this home of WB by this smaller subspace. And so, and then you have this vector space, and if you move all B, image of B in the space of Grassmannian, so from this description, this space home of BW divided by image B is tangent space, and we are considering dual space of the tangent space. So it means the total space. So if we move all points in the Grassmannian with union of this cotangent space, this is a total space of cotangent band of Grassmannian manifold, which is usually denoted by T star of Grassmannian. And in particular, it is a symplectic manifold. We have the original tangent direction of the Grassmannian, and we add the cotangent direction. So then each tangent space is a symplectic vector space. So this is a symplectic, and also you can show that this natural symplectic structure is closed, and this is a symplectic example of symplectic manifold. Okay. So in this particular example, you can rather easily get to the correct notion of the quotient space in symplectic geometry. And note that this, as I said, this home of WB is a bigger space which is not correct, and we must replace it by this one. And the condition of A descent to this homomorphism is nothing but the equation A times B equals 0. And we see this AB as an example of moment map, which I now more introduce in more generally. So I define mu map mu from M of VW to the dual space to the algebra of G, and I identify the real algebra of the dual of the real algebra of G by twice pairing with the real algebra of G. And the formula is like this. So that the formula is generalization of this A times B. So for each vertex I, so this first of all, maybe I forget to write that. But the real algebra of G is just the direct sum of the all real algebra of G and Vi. So because G is a product of G and Vi's. So it means that for each I, we have the endomorphism. This is the real algebra of G. So in order to define the map, I just need to define I just need to define each component for I, And this is given by this formula. So first part is epsilon h is plus minus 1. So if h is in the original quiver Q1, then epsilon h is plus 1, and h is in the opposite quiver, then epsilon h is minus 1. And BH times BH bar. So maybe if this strange sign is somehow it comes from the definition of the symplectic form, which I didn't write down explicitly. But you have the n product out. So m is direct sum of n and n star. And if you change the order of n and n star, then symplectic form change the sign. So this is the reason why we need to put the epsilon h. So except that point, the first component is analog of A times B. I just replace small a by B of H and B by B of H. And this component is just the direct generalization, small a times small a. Then, as in the case of the example of the simplest quiver, so kernel, if you just consider the kernel of d mu, then this becomes a symplectic vector space, at least under the assumption that d mu is surjective and the kernel of d mu. Sorry, maybe I make a mistake. So you first consider mu, and then consider the differential d mu, and then you consider its kernel. So if d mu is surjective, then this is a subspace in the space of this MVW, which kills the redundant direction. And can I go back? Yeah, I said that this, if you just consider this, take the whole vector space, so you have the redundant direction perpendicular to the tangent to the orbit direction. And but if I replace this by the kernel of d mu, then this becomes symplectic vector space. And if you compute the dimension, so this I replace this by kernel of d mu, so this is dimension is decreased by dimension g, and I take the quotient by this orbit direction, and if the orbit is also nice space, and for example, this is if this the action is free, then tangent space to the orbit has also dimension equal to dimension g. So in total, this if I replace this by the kernel of d mu, then total dimension is decreased from m of vw by 2 times dimension g. So if the original space is even, then the result is also even. So at least in this condition, it's satisfied. And also you can show that this quotient space is symplectic. So in order to have this space as a tangent space, we impose the condition that mu is equal to 0 in MVW, and then take quotient. So this space is called symplectic reduction. And you can slightly generalize the condition that instead of 0, you can take the sum of scalar matrices. So zeta I is scalar. And you can impose, instead of mu is equal to 0, you can also impose the condition of mu is equal to this direct sum of scalar matrices. And then this element, so maybe I should also point out that this mu inverse 0, because so you must check that how mu changes under this conjugation action. But if this is 0, and if from this form, so even if you change B and A and B by the conjugation action G, the value of moment map is under. And if the moment map is 0, then the conjugation action resolve the mu of this equation equals 0. And the same holds for this identity case because the identity element is fixed by the adjoint action. So this value is changed by the adjoint action. Okay. For example, if for A times B, the action is GA times BG inverse. So A times B is changed by G times B times G inverse. So this is conjugation, adjoint action of G to the A times B. Okay. So this quotient space, you can consider, because of this, the moment map equation is preserved, so you can consider the quotient space. And by general machinery in symplectic geometry, general theory in the symplectic geometry, which I just explained only the point of the argument. So you can show that this quotient space is a correct quotient space in symplectic geometry. So this is called symplectic reduction. Okay. So any question so far? Okay. However, this quotient space is not yet the correct quotient space. So this is already illustrated in the example, which I explained in the beginning. So I described T star of Grassmannian as an open subset in a quotient space because we impose this condition, injectivity of B. So if we drop this condition, so we get a larger space, which might contain this T star Grassmannian, but we must somehow need to understand those which is removed when we impose this condition. Okay. So this issue already appears without going to symplectic geometry. Even I take only the second component and the quotient space. So this space, if B is injective, as I mentioned, this is a Grassmannian quotient space becomes Grassmannian manifold. But if we don't impose injectivity, then the quotient space is something different. And in fact, this is a delicate question because so this is type. So this is quotient space, not the question space. Quotient space, in general, not the Hausdorff, or it doesn't have a structure of manifold. So when you want to deal with quotient spaces, somehow you must be careful. So this happens quite often in various study of quotient spaces. And there are several approaches to overcome this problem of non-Hausdorffness. So first approach is just to extend the notion of spaces. So instead of quotient space as a naive space, you somehow extend the notion of spaces. So maybe some of you heard about the notion of stacks. So stack is a correct language to discuss those kinds of quotient spaces. But today we don't use this terminology, this notion of stacks. We don't try to extend the notion of spaces. So we just want to deal with the quotient space as usual space. One of the reasons is that we want to consider the topology of the space. And the topology of space is changed if we extend this notion of spaces to stacks. And in fact, if just we define the quiver variety as stack, then the result, which I will going to explain, just fails. So it's just the fact that the quotient space, you can use the stack, but this in this particular case, you don't get the correct space if we just use the stack. Okay, and this is the reason why I don't take this approach today. And the second approach and the third approach are the approaches which I will use today. So the second one is which I already explained. So I just restrict to open subset, like B is injective, and this is called geometric invariant theory quotient. So geometric invariant theory, in geometric invariant theory, you don't consider the naive quotient or stack. So you just take open subset of the original space and take the quotient. Then you can expect how to somehow remove this non-Hausdorffness, or you can hope that the quotient space to be nice space. So not only in symplectic geometry or the theory of Quiver varieties, GIT quotient has been used in various places, and so maybe some of you already know about it. But today, somehow, I don't intend to discuss the general theory of general introduction to geometric invariant theory. So I will just introduce the definition of the generalization of this injective condition in the next page, and I will not explain where this definition will come. So if you are interested in geometric invariant theory, then, for example, it is discussed in detail, or maybe the correct references are given in the textbook of Kirillov, which I mentioned in the beginning. So I will not explain it today, but this is very interesting subject, and but for the sake of time, I will not explain it today. Okay, this is the second approach. And the third approach is replacing the quotient space by set of all closed G orbits. So this non-Hausdorffness basically comes from the existence of non-closed orbit. So if you have the orbit, and it contains the closure of the orbit, and if two orbits intersect, if take two orbits, which is a different point in the quotient space. But if you take the closure of the orbit, then they might intersect. In that case, in the topology, quotient topology, you cannot separate those two orbits. That is the reason of the failure of non-Hausdorffness. So if you just consider the set of all closed orbit, G orbits, so you just forget to open those non-closed orbit and just consider closed orbit, then this problem disappears. And this set of all closed G orbits are called categorical quotient. And also this also appears in geometric invariant theory. So we use this second and third approach in the theory of Quiver varieties. So I already explained the second approach for the case of the simplest case of this one simplest quiver of one vertex without no edge. So I next study the third approach in this example. So this case, A times B. So I assume the B is injective in the second approach. So let us try to drop this condition. So for example, so let us consider the extreme case, B equals 0. And then let us study what is the closed orbit in this case. So take GT to be T times identity of B, and I multiply G of T to A and B. So this is a conjugation action. And I assume B equals 0. So in this case, this is just the GT times A and 0, and GT is T. So this is T times A. So if B is not 0, or you have B times T inverse, then you cannot take the limit to T goes to 0. But because we assume B equals 0, the second component just vanish. So you can just take the limit when T goes to 0. And this goes to 0, 0. So it means if A is not 0, then in the limit, you get to this. By the way, so this 0, 0 consists of single orbit, single point consists the whole orbit. This is fixed by the action. So this is a closed orbit because other orbit, you cannot move this. And the other orbit, A non-zero, it doesn't have closed orbit because of this consideration. Okay. So it means if there are many orbits, B equals 0 and A could be non-zero, but if I just restrict my interest to the closed orbit, then A is automatically 0. And more generally, so if B is not necessarily 0, then you can embed the space of all GLB orbits into the space of endomorphism of W by considering X given by B times A. Okay, so for each point AB, bracket AB in this quotient space in this sense, the space of closed orbit. So this means that I take the closed orbit passing through A times B. So you assign X equal to B times A. So this is a closed embedding, and this is the consequence of fundamental theorem in invariant theory. And for example, if B equals 0, then X is always 0 for any choice of A, right? So in that sense, somehow because of combining with this consideration, somehow I hope you see that this is a good embedding to describe the closed geometry. And also because I impose a condition mu equals 0 for MBW, so it means A times B equals 0. Then because of this definition of X square is equal to BA times BA, so which is 0. Okay, so you get square equal 0 matrix. And in fact, you can show that the space of closed GLB orbit in mu inverse 0 is space of endomorphism, a space X of endomorphism W, whose square is equal to 0, and the rank of X is smaller than or equal to dimension B. So this is a description of the quotient space as the set of the replacement, third approach for the correct quotient space of mu inverse by GLP. So these two approaches can be applied for more general quiver. And as I said, I just give you the definition of the analog of the condition for the injectivity of B. So this definition might look artificial a little bit, but in fact, this is naturally come from the geometric invariant theory, as I mentioned. So in order to understand the actual meaning of these conditions, somehow you must study the geometric invariant theory. But for this, for today, I just introduced this definition, and please accept this as this definition. So anyway, so let me introduce. So I take a point BAB satisfying the moment map equals 0 equation, or maybe you can consider the same condition for arbitrary point in beta. And I say this is stable if this condition is satisfied. So there's no non-zero subspace of B, which is compatible with the grading Q0. So which I just mean the S is a direct sum of SIs for each vertex I. SI is a subspace of BI, such that this is invariant under the B, and also S is contained in kernel of B. So in other words, if there is such a subspace, S must be 0. So this is a condition. And if the Q is just a single vertex without any edges, then the first condition is redundant, and we only have the this second condition. So there's no subspace in kernel B, but it just means B is injective, right? So this recovers the injectivity condition for B if Q is the simplest Quiver. And I denote mu inverse 0 of ST as a set of stable points BAB in this level set of the moment map. And this is an open subset, open in the both in the Zaleski topology or classical topology. Right? If you have BAB and if you slightly perturb BAB, then this condition is present. And then you take the quotient space, mu inverse 0 of stable by G. And geometric invariant theory guarantees that this quotient space is nice. And yeah, by general theory, this might have the finite quotient singularity, but in this particular case, in fact, you can show that this is a smooth space. So this is a manifold, complex manifold. So this is the definition given of the quotient space given by the second approach. Okay. And then for the third approach, as I said, this is the categorical quotient, which is the set of closed orbit in the universe. Okay. Yeah, this is a remark which I just explained. So if the quiver is trivial, then this stability condition is same as the injectivity. And there are some basic facts from the geometric invariant theory. So if you take the orbit of the orbit and consider its closure, then it is a union of orbits. So there you have some smaller orbit appearing in the closure of the geo. And there is a unique georbit in the closure, which well, maybe unique orbit which is closed. Maybe sorry, I did this is not explained properly. So we have the unique georbit which is closed in the closure of georbit. This is the smallest orbit. So then from this consideration, we have a natural morphism of mechanism. So this maybe I emphasize this note. I forget to emphasize this notation. I denote this quotient of a stable point divided by G by MBW in this way. And I denote this categorical quotient by M0. So I will use these notations from now. So please remember these notations. So this is the set quotient space of the stable point by G, and this is the set of closed orbit. And if you have orbit, GM, then from the which I just explained, so you consider the closure of this orbit. And as I said, there's a unique closed G orbit in this closure of the orbit. So I assign the corresponding closed G orbit to G of n. So by this way, we have a natural map from this quotient to the second quotient, right? So M to M0. And in the simplest example, so the first quotient is a cotangent bundle of Grassmannian. So this is a set of A times A and B's. And the second quotient is, as I just explained, the space of linear maps X, whose square is equal to 0 and rank is smaller than or equal to dimension B. And this map is again this given by just extending the map which I used in the identification of the quotient space with X. So that's namely it's just given by X is equal to B times A. Okay. Then you can study the property of the map pi in this particular example. For example, so suppose from this subset target space, you consider the point where the rank of X is equal to dimension B. Right? So in general, rank could be dropped from is smaller than dimension B, but I just take this form open subset. They take the point where rank of X is equal to dimension B. Then image, so if this is satisfied, the image of B is equal to image of X. So this cotangent band of Graxmannian is a pair of the imaginary part E and the homomorphism in this direction. And this image of B is recovered from X as image of X. So this point is determined. And also this component, the cotangent direction, is also recovered from X. So it means that if I take a point X, which satisfies rank X equal to dimension B, then the inverse image is a single point in the cotangent band. So more generally, you can show that this is a resolution of singularities. So this open subset consists of rank X equals to dimension V is non-singular point of this target space. And if you drop that condition, it is a singularity. And you replace this space by some smooth space such that this open subset of smooth point is not replaced at all. So this is a notion of resolution singularities. I will not use a resolution singularity in this talk, but somehow this illustrates the relation between these two quotients, MVW and MZBW, right? And I didn't explain properly this condition, why I need to assume 2 times dimension B is less than or equal to dimension W. But for example, if dimension B is too large, then you cannot have this equality. Rank of X, in order to having the rank of X is equal to dimension B. So for example, X squared is equal to 0. And so because this is nilpotent, X cannot be full rank, for example. So if V is too large, then rank of X cannot be dimension B. So in that sense, you should have some condition, but in fact, in this case, you can a little bit more carefully analysis. You show that this condition must be satisfied. Okay, so in this case, this equality is non-empty open subset in here, and you show that this is resolution. And from geometric invariant theory, you can derive several properties of M and M0. So first of all, both are algebraic varieties. So it means that this is object of algebraic geometry. So you can use various results in algebraic geometry. So I will use some result of them, but not explicitly. So mainly I only consider M and M0 as a topological space, and in particular I will consider their cohomology groups. So I will not do superficial. I don't use any result from algebraic geometry, but in order to prove some statement, in fact, I will use. But I will not explicitly mention how I used. And the second is more important. This M, the quotient of the stable point IG, is a smooth space. So it is, in particular, this is a complex manifold. And the third point is this space morphism, natural map pi from M to M0 is a projective morphism in the sense of algebraic geometry. But in practice, for application which I will explain today, we only need this property for the usual topological space. So it means just this morphism is a proper morphism in the sense of general topology. So it means that the inverse of the compact subset is also compact. Right? So this is the definition of proper map. Maybe I should also say pi is a continuous map, but also this is a proper map. Okay, this is a consequence of the general result from geometric invariant circuit. And later I will use the action of the two groups which I so far didn't mention at all. So maybe return back to the So I introduced three groups, G and GW and C star, and I take the quotient of MVW by the first group G. But you have the additional group action GW and C star on MVW. And this action commutes with the action of the original group G. So because of this commutativity, this second and third group acts on the quotient. This will be used after. Okay. And this pi is equivalent, means that if I consider the action on this M and consider the action of M0, then the action is compatible with this map M. Okay. So now I give the example of Quivers variety, which is slightly more complicated than the trivial example of the cotangent bundle glass manion, which I mentioned. So I consider two vertices, 1 and 2, and I draw arrow like this. Then I consider the corresponding Quivers varieties, which consists of those linear maps, and I assume that all those vector space are one-dimensional. So I have linear maps B1, B2, and the small a1, B1, the small a2, B2, like this. So let us determine the Quivers variety in this particular examples. So the categorical quotient is easy, and in fact, you can just like in the case of BA for the trivial example. So I consider the composite of linear maps starting from some vector space in W1 or W2 to W1 to W2. So I have three such possibilities. So first one is X, which is the B2 times B1 times A1. So A1, sorry, B2 times B1 times A1. So this is a linear map going in this direction, right? Starting from W1, and then going to V1 and V2, and then we end up with VW2. So if you consider such linear maps, so this is invariant under the conjugation action, and this will gives by the result from the invariant survey. This kind of definition gives an embedding of the categorical quotient to some vector space. So this is the first element. And you also consider the similar one, Y, which is B1, B2, A2. So this is a composite of linear maps like this. right? Starting from W2, you consider that with W1. And G is just starting from W1 and then by going to B1 by A1 and then return back by B1. So G is B1 times A1. But by the equation mu equals 0, and you must, I'm not sure the plus minus sign is correct, but anyway, so this A1 times B1 is equal to B1 times B2, and B1 times B2 is equal to A2 times B2. So I always consider this W1 mapping from W1 to W1, but this is equal to all other maps. Then, so this is not independent variables, and if you multiply x times y, then this is, you just get B1 and A1 and large B1 and large B2 and small B2 and A2. So it means that you get the Z to the 3, right? XY is D to the Q, D to the 3. So X and Y and Z gives embedding of this categorical quotient in this vector, three-dimensional vector space. But in this case, it's not the whole three-dimensional vector space. The equation is just given by x, y is equal to g3. And this equation is it gives a hypersurface in the three-dimensional vector space. And this is the famous A2 type singularity. And this is not the accident. This A2 singularity appears from this A2 quiver. So this quiver is called A2 quiver. And if you consider this kind of variety, quiver variety, for A2 quiver, you get to this A2 singularity. This can be generalized. So you can identify the categorical quotient for AN more generally with AN type singularity. So next, let us go to the GIT quotient, which is M, quotient of stable point by the group. So in these linear maps, the condition of the stability means that you cannot have B1 equal to 0 and B2 equal to 0 simultaneously. So this is a condition, one of the condition, consequence of the stability condition. So M is a union of B1 non-zero and B2 non-zero. Then take up, so and both open subset in M. And let us take the point, the open subset where B1 is non-zero. Then you can normalize. So I take the quotient by GLB1 and GLB2, and in this case, this is just the C star. So by the action, and I assume B1 is non-zero, so I can normalize B1 to be 1. Then I have the remaining maps, B1, large B1, B2, and small a to B2. And this small a1, once B1 is equal to 1, we have equation a1 times B1 is equal to large B1 times B2. So B1, since B1, I normalize B1 to be 1. Small a1 is just B1 times B2 from this equation, right? So I can forget the small a1 because of this. So then after normalization, I just get to this space, and I still need to take the action by general linear group of B2. But if I combine this V1, W1 into a single vector space, then it is just the example of the corresponding to trivial quiver. So I have a single vertex, and if I combine V1 and W1, then this is a framed vector space. Then the framed vector space, after taking direct sum, this becomes two-dimensional space. And so it was the cotangent bundle to Grassmannian, but in this case, this is the just project line. So this quotient space is just T star of P1 by the previous consideration. And concretely, you can write down the coordinate, homogeneous coordinate and cotangent direction in this way. So I have, so the map from B2 to V1 plus W1 is given by B2 and small B2 and large B2. So this going to this direction and this direction. So this gives a homogeneous coordinate of P1. By the stability, it cannot be simultaneously zero. And the cotangent direction is opposite than the H. And similarly, if you consider the open subset B2 is non-zero, then you can normalize B2 equal 1. And then you get again T star P1. So this T star P1 and this T star P1 are different, and M is covered by these two T star P1s, like this picture, right? So this B2 equal 0 is removed in this first open subset, and B1 is equal to 0 is removed in this, maybe, sorry. So B2 equals 0 is removed in the second open subset, and B1 equals 0 is removed in the first open subset. And this P1, 2P1, red P1, and blue P1, this cotangent direction vanishes. So for example, red one, A2 and B1 is equal to 0. And from the equation, you can automatically deduce small a1 is equal to 0 in this case. And for blue one, A1 and B2, so this A1 and B2, these two linear maps vanish. And A2 is also. So this is the picture. You have two P1s intersect, and also you can study the intersection. So intersections are like given by those linear maps. So most of the linear maps are 0, but except this B1, B2. You can check that this linear maps satisfy the stability condition of this. So you have two P1, red P1, the blue P1s. They intersect at a single point like this. And if you draw a Dinkin diagram corresponding to this configuration of P1, so you put the vector space, vertex to this red P1 and vertex for this blue P1. And if they intersect, P1, corresponding P1 intersects, then draw an edge between them. So this is in this way, you can recover the type A2 Dinkin diagram, and that is one of the reasons why this singularity is called A2 type singularity. So this A2 singularity type singularity has resolution given by this M, and this is so-called minimal resolution of this A2 type singularity. So this is some canonical resolution singularity of A2. And the configuration, so then the inverse image of 0. 0 is the only singularity of this M0. The inverse image of 0 consists of two union of two P1s which intersect at the point. And if you draw a configuration diagram corresponding to this configuration, you get a type Dinkin diagram, Coxeter Dinkin diagram. Any question? Yeah, so this is what just I explained. So the type of singularity A2 is coming from this configuration of the exceptional set. Exceptional set is the inverse image of the singularity of this, in this case, origin. And the exceptional set is a union of the P1s. And if you draw the diagram corresponding to that, you get the Dinkin diagram. And this Dinkin diagram is the same as the underlying diagram for the original quiver. So in this original quiver, I have oriented edges, but for Dinkin diagram, I forget the orientation and just replace this oriented arrow by just unoriented arrow. So this is a Coxeter Dinkin diagram. So the type of singularity is just given by forgetting the orientation of the original quiver. And this is more general, so I mentioned the type AN case, but for type D and type E, so you consider the type D or type finite type linking diagram and put some orientation, and then consider appropriate choice of dimension vectors. You can get M0 as the type AD singularity and its minimal resolution. Well, D and E is a little bit more complicated. For example, if you can play with the example of type D4 singularity, and this is something non-trivial. Okay. Let me see. Maybe at some point, do I need to take a break at some point?
It's up to you if you want or not. You can continue.
Let me see. Okay, let me continue a little bit and take a break. So this is one of the one of most important geometric result about the quiver variety. So suppose Q has no edge loop. Edge loop means that the edge which connect the vertex to itself, the same vertex. So I exclude such edge loops. I assume that Q has no such loops. Then pi inverse of 0. So 0 is means a distinguished orbit, closed orbit in this MVW. So all the linear maps is 0. Then this is clearly 0 in the closed orbit. And I consider that the inverse image of 0 in this natural map from MVW to M0VW. So then this is a Lagrangian subvariety in MVW. So the MVW is a symplectic manifold, and the pi inverse 0 is Lagrangian subvariety, which means that if you restrict the symplectic form into pi inverse 0, it vanishes. So this is a Lagrangian subvariety condition. And pi inverse 0 is homotopic to MVW. So if I'm interested in the topology of MVW and the particular cohomology or homology of MVW, then pi inverse 0 is homotopic. So you can replace MVW by pi inverse 0. So in that sense, pi inverse 0 is the most important part of MVW. The pi inverse 0 is meant by L of VW because this is Lagrangian. And I gave two examples. So the trivial quiver, I get a T star of Grassmannian, and the inverse image of 0 in this case is just cotangent direction vanishes, which is the set of all Grassmannians. So this imaginary image of B, I still have the image of B, but the cotangent direction is 0. So this is a space of 0 sections. And this is a Lagrangian subvariety in the cotangent band. And in the second example, which I just explained, pi inverse 0 is a union of two P1s, blue P1, red P1. And I just explained that this gives the H type linking diagram as a configuration space. And in that sense, this is how to say most important part of this resolution. And then this remark just says that if I drop this assumption, then in general, this is no longer true. But anyways, also I will not talk about example which doesn't satisfy in this condition afterwards. So maybe just detail. So anyways, without this assumption, this result is not true in general. Okay, let us take a break now and let's resume in 5 minutes. Okay.
Okay, cool.
Okay, I now start to talk about the relation between the quiver varieties and the representation theory. So we as I said, we assume that there is no edge loop hereafter. So starting from Quiver, as I already mentioned briefly, I get a linking diagram by forgetting orientation edges. Then I can consider the corresponding Kac-Moody real algebra classified by this linking diagram. So concretely, so if C is a Cartan matrix, Cij, if I equal 0, I equal j, this is 2, and if I and j are different, then it is the sum of number of edges from I to j or j to I. So if I start with A2 quiver, which I just introduced in the example, I get to the usual A2 linking diagram, and the corresponding real algebra is SL3 in this case. And if I start with the trivial quiver, so one vertex without edges, then linking diagram is A1, and I bring it to SL2 as a real algebra. Then the goal is by using the quiver varieties, I will construct integrable representation of the real algebra. Okay. So in this way, I get the representation, but from this construction, G is symmetric because the symmetric, what do I mean by symmetric? So Cartan matrix, by this definition, if I change I and j, exchange j and I and j, this is, I consider the sum. So the sum is unchanged even if I replace I and j by j and I. So this is C Cartan matrix is symmetric. In this sense, this Kac-Moody real algebra is automatically symmetric. So for example, in the finite type case, I can get ADE type real algebras, but I cannot get, for example, type B real algebra. So it is still open problem to develop a theory of quiver varieties for non-symmetric Cartan matrix. So quiver variety has been introduced many years ago, already maybe 30 years ago, and this is open from the beginning of the introduction of quiver varieties. So in the slightly different setting, I recently studied the so-called Coulomb branches, and the Coulomb branch can be defined for, again, starting from this quiver together with this vector space V and W. And in this case, together with weakest, we find some way to get to define Coulomb branch for non-symmetric ones. So it's but this construction is not general to the original definition for quiver varieties. So in that sense, this is still open. So anyway, so I briefly recall the definition of the Kac-Moody real algebra. So this G is given by generator and relations, and the generators are those. So H, which is usually called Cartan subalgebra, and this is some complex vector space, and the dimension is equal to number of vertices in the graph, and also you add the dimension of column C. So I'm only basically I only consider finite type case, and then the C is invertible, so the second summand is 0 and the Q0. So dimension of Cartan matrix is equal to just dimension the number of vertices. And in the dual space of H, I have alpha i's, which is called simple roots, and for each vertex I. On the quivers, I have alpha i's, and I also have co-roots, simple co-roots HI for each I in the vertex, and I assume those alpha i's and HI are linearly independent and satisfy the equation. The pairing between HI and alpha j is equal to Cartan matrix. And because of this assumption, this embedding is possible. And this is a part of generators. H is part of generators, but I have additional generators EI and FI for each vertex I and satisfying certain relations. I illustrated the I gave only most important ones. H bracket D bracket of H and EI is given by this simple co-root alpha I times H applied to H, and this is a scalar and multiplied to EI, and similarly for H and Fi. And if I take H1, small h1 and small h2 from the Cartan subalgebra, this they are commutative, they commute. And if I take the bracket of E and Fj, then this equals delta ij times hi. And there are other relations called cell relations, but I will not review what they are. And the goal is, as I said, I want to construct a representation from MVW. And a little bit more precisely, I take the cohomology group of MVW, or more precisely, cohomology of MVW and take direct sum over all those B's. And then I introduce operators EI and FI and H's, and they satisfy those defining relations. So this is how I construct the action of the representation of the real algebra on the cohomology of MVW. So if you know that the standard construction of the representation by geometry, so which is the Borel-Weil theory, you start with the flag variety and consider the group action and take some line bundle and consider the space of sections of line bundles, and you have the action on the space of sections, and this realizes the representation of the group and take differential, you get the representation of the real algebras. So this is again the construction by Quivers variety is again by geometry and cohomology, but the cohomology is here is a topological cohomology, and for Borel-Weil theory, you consider space of section. This is an example of Dolbeault cohomology, and Dolbeault cohomology and the cohomology of the ordinate space both are cohomology groups, but they are completely different. So in that sense, somehow constructions are very different, and also the flavor is very different. It is very crucial that we use the disconnected space. We take the direct sum of MVW over all these. So this is one important feature in this construction. And for the Borel-Weil construction, so we just use a single space flag variety which is connected. So this is a big difference. Okay, let me start with the simplest case again. So the one single vertex without edges. So in this case, the real algebra is SL2, as I said. And in this case, the classification of finite dimensional irreducible representation is just given by integers. So I consider the R plus 1 dimensional irreducible representations. Irreducible representation, this is unique. And this is illustrated. The representation is illustrated by this picture. So each dot corresponds to vector in R plus 1 dimensional vector space. So there are R plus 1 those circles, those dots. And F and E sends this vector to second vector and third vector and so on. E goes in the opposite direction. And H, those dots are eigenvectors for H. And the leftmost vector is called the highest weight vector, which is killed by E because there's no arrows written here. So it is killed by E and sent by F, and all other vectors are obtained from this dot. And moreover, it is, so as I said, this is an eigenvector, but it is better to normalize this eigenvector carefully. So this is an integral structure hidden in this representation. And in this case, just rather than just sending V0 highest weight vector by product of F's, so I divide by the factorial, K factorial. So this is a standard eigenvector in this eigenspaces. And then you can write down the corresponding operator H and F and E explicitly in those VKs, and this is the formula. And there's some coefficient R minus 2K and K plus 1 and minus K. And the K runs from 0 to R. And V minus 1 and VR plus 1 is equal to 0 by convention. And for example, if I take K to be R plus 1, then this coefficient vanishes. So VR plus 1 must be 0. So EVO of VR plus 1 must be 0 also. So this is compatible with this coefficient to be 0. And the similarities. -1, K equal -1 this coefficient to 0. Okay, so in that sense, these coefficients are, of course, you can compute them, but these coefficients are somehow important to having these R plus 1 dimensional representation. So this is the first construction of a representation method you run in the very beginning of the representation, study of representation of the complex simple reals. So I want to realize this as the cotangent bundle of Grassmannian, because in this case, the corresponding equivalent is cotangent bundle. So I take V to be K-dimensional space and W to be R-dimensional space. Then this is cotangent bundle. Then maybe I didn't carefully explain that in order to this space to be non-empty, K must be between 0 and R. If K is larger than R, then of course, this is a Grassmannian of subspace, K-dimensional subspace in C to the R. So K cannot be larger than R. So it means that this right-hand side is empty. So in total, you have R plus 1 non-trivial spaces. And so if you consider the cohomology of the cotangent bundle of Grassmannian, so because this is a vector bundle, this is by Thoma isomorphism, this is isomorphic to homology group to Grassmannian. And I choose top degree cohomology of the Grassmannian. So top means that this is Grassmannian is a complex manifold whose dimension is equal to K times R minus K. So in particular, this is as a real manifold, this is 2 times K R minus K dimensional manifold. And by Poincare duality, so the top degree part, if I take this dimension, real dimension of the manifold, then the homology group is one-dimensional. And this is spanned by the so-called fundamental class. So I take this one-dimensional space. Then this matches with this picture. I have one-dimensional space, R plus 1 one-dimensional space for each corresponding to each this dot. So we want to make, we want to identify this vector Vk with this fundamental class. Then if I succeed to define those operators F and E in a geometric way, it means that we can realize this representation in geometry. Okay. And there's a standard way to construct such operators E and F. So this is the technique of the correspondences. So if you have a map between the space topological spaces, then you have the induced map between homology groups and the cohomology groups. So for homology groups, if you have a morphism from X to Y, then you have a homology for X to homology to Y, and for for cohomology in the map in the going to opposite direction. But the correspondence is more general than these homomorphisms induced from the continuous map. So this is given by this diagram. So I consider the k-1 dimensional subspace in R-dimensional space, the Grassmannian, and also k-dimensional subspace in R-dimensional space. And I connect those two Grassmannian in the intermediate space. So this I denote by Q of KR. So this consists of pairs of vector spaces S1, S2 in CR. So S1 is k-1 dimensional, S2 is k-dimensional. So this, you can consider this Q of KR as a subspace, submanifold in the product of this product of two Grassmannians, k-1 R and KR. Then so here secretly I use the fact that all those three spaces are smooth in particular, so I have Poincare duality. So you can use both cohomology and homology groups. And as I said, if you have a map, continuous map, you can push forward homomorphism between the homology group and pull back homomorphism for the cohomology group. But because we can use both homology group and the cohomology group by Poincare duality, so you can have map in, you can use both pullback and push forward. So you start with this H star smaller Grassmannian. Then you first use the Poincare duality to replace this homology group by cohomology group. Then I can pull back by Q1. So this is Q1 upper star. So this is a pullback in the cohomology group. So I secretly use the Poincare duality from identifying the homology group by cohomology. And then on QKR, so I get the cohomology group of QKR, but again, QKR is smooth. I use the Poincare duality to identify with this homology group of QKR. Then I push forward by Q2. So because this is a homology group, I have a map to the homology group of Grassmannian QKR. And I have the homomorphism in the opposite direction. I first start with homology group in here, and then I consider it a cohomology group by Poincare duality, and then pull back, and then return back to homology group of QKR, then push forward Q1. So I have two maps in both directions going to this direction. So this is the first candidate for the linear maps, E and F. But in fact, it turns out this correspondence is not a correct one. For example, so maybe I didn't emphasize, but so if I consider the total homology group, this is much larger than one dimension. So since I want to have one dimensional space correspond to each dot, so I take the top degree part of the homology group. So by this correspondence, I didn't carefully examine how this degree is shifted, but this Q1 star and Q2 star, because I mix the Poincare duality, I use more Poincare duality twice. So this degree is not preserved. In particular, top degree is not preserved in this correspondence, these maps. So in that sense, these maps are not the correct one. And in fact, I emphasize that the Quivers variety is a symplectic manifold. So this correspondence doesn't reflect this symplectic geometry at all. So there's natural correspondence in symplectic geometry. So this is the conormal bundle construction. So concretely, so I replace this Grassmannian by cotangent bundle of Grassmannian. So I add the cotangent direction like this. But so this in the intermediate space QKR, I also add the cotangent direction. But somehow this cotangent direction should be somehow in the middle of this cotangent direction for the first Grassmannian and the second Grassmannian. So the first Grassmannian, so for subspace, so if the subspace is S1, then the linear map goes from C of R divided by S1 to S1, right? And for the second CR divided by S2 to S2. So we should have something in between. Then basically I only have one candidate. So the domain I take CR divided by S2. And for the target, I take S1. So I consider the homomorphism from CR divided by S2 to S1. Then, because of this condition, S1 is a subspace in S2. So I can compose the inclusion from S1 to S2. So if we have C in this homomorphism, I get the element in here by composing inclusion S1 to S2. So then you have natural morphism, natural map from this intermediate space to cotangent bundle to Grassmann. And similarly, so because S2 is a larger space, if you have element in here, I can compose the natural homomorphism from CR divided by S1 to CR divided by S2. So then I get the homomorphism from CR divided by S1 to S1. So this is the cotangent direction for the first Grassmann. So I have a natural map from this intermediate space to cotangent bundle to Grassmann. And in fact, this is natural construction in symplectic geometry. So if you have a product in the, consider submanifold in the product of Grassmannian, then you can naturally define the Lagrangian submanifold in the product of cotangent bundle to Grassmannian. So this Lagrangian subvariety is a cotangent, co-normal bundle. And this is, concretely, this is given by just this construction. Then you can define the homomorphism just in the same way. So because these spaces are non-compact, so you must, when you apply the Poincare duality, you must be a little bit careful. So you must you use a cohomologous compact support for the Poincare duality. But otherwise, the construction is the same, right? So this is a result of Ginsburg. So I consider this pullback push forward and pullback push forward for in both directions. And I multiply some scalars, some signs, and take the sum over all those cases. I consider all the Grassmannians. Then this realizes R plus one-dimensional irreducible representation of SL2, so that Vk is given by the fundamental class of the Grassmannian. So let me check that the top degree part is preserved for this pullback and push forward. So let me carefully check how degrees shift. So the homology group of cotangent bundle Grassmannian is Poincare dual to the cohomologous compact support, and the degree, the sum of the degree must be dimension of the real dimension of the manifold, which is 4 times D2. D2 is the dimension, the complex dimension of this Grassmannian manifold. Because cotangent bundle is twice dimension, and as a real manifold, again, you must multiply by 2. So in total, you have 4 times the complex dimension. And if I start with top one means that 2 times D2. So this star is 2 times D2. Then because 4D2 minus 2D2 is 2D2. So then I get again 2D2 in here. And then I use the Poincare duality. After pull back to the intermediate space, I use the Poincare duality to go back to homology group. But if this is equal to 2 times D2, and the PKR, intermediate space is, as I said, it is a Lagrangian subvariety. So whose dimension is a half of the dimension of the product of Grassmannian. So in this case, I also did not introduce D1, which is the dimension of Grassmannian minus R. Then the dimension of this intermediate space is D1 times D1 plus D2. So cotangent bundle is T2 times D2, 2 times D1 plus 2 times D2, and this is Lagrangian, so you must divide by 2. So this is D1 time plus D2 dimensional. And as a real dimension, this is multiplied by 2. So I have this number. And as I said, if I start with 2 times D2 here, then I get 2 times D2. So this is 2 times D2. Then it means that this is 2 times D1. Right? So this form. Then I push forward. So it means that starting from 2 times D2, top degree homology group of Grassmannian, then I end up with the top degree homology group of Grassmannian. So because of this reason, somehow, as I said, Q1 for original correspondence, this degree is not preserved, top degree is not preserved, but if I replace natural correspondence in symplectic geometry, this degree is preserved. And a little bit more carefully, so we must use compact cohomologous compact support. So you must have a pullback for the compact cohomologous compact support. So I use the fact that the P1, P2 is proper. So this is one of the consequences of this properness of the morphism from M to M0. And this is guaranteed. So this pullback is well defined for cohomologous compact support. So in this way, these maps homomorphism are well defined. Then once this is defined, I mean, of course, maybe you don't see the philosophical reason why you should define this map in this way of correspondence. But anyway, so this is very natural construction. So it is natural to study the meaning of these operators. And if we once accept this definition, the only remaining argument for the proof is to recover those coefficients appeared in this explicit formula of f of vk and e of vk. So somehow you need to recover those coefficients k plus 1 and r minus k plus 1 from geometry of this correspondence. So that is the heart of this result. And in fact, these two numbers appears as Euler numbers of the fibers of those of projection of the first naive correspondence for this Q of KR. So let me examine what are the fibers of this morphism of Q1 and Q2. So what is the fiber of Q1? So I fix subspace S1 and I move all S2s. Then what is the possibility of the choice of S2s? So S2 is a subspace in CR, but I fix S1. So in particular, I can replace S2 by the quotient of S2 divided by S1. So because this is a k minus 1 dimensional space and S2 is k dimensional, quotient S2 divided by S1 is a subspace, one-dimensional subspace in CR divided by S1, like this, right? So this is a Grassmannian manifold of one-dimensional subspace in the quotient space. And this CR divided by S1 is R minus K plus 1 dimensional space. And this is a projective space, complex projective space, and whose Euler number is well known. This is, if dimension is R minus K, the Euler number is one larger one. So this is R minus K plus. Similarly, for the fiber of Q2, I fix S2 and I consider the all possibility of S1s. Then this is a k minus 1 dimensional subspace in k dimensional space. Then this is again projective space of k minus 1 dimensional complex projective space, and Euler number is equal to k. So if you compare this previous coefficient, then they are almost the same. So this is r minus k plus 1, k plus 1. The only difference is k plus 1 is replaced by k here. But this is natural because, so this is k minus 1 k. And in this previous coefficient, so I use k and k plus 1. So I must replace k by k minus 1 in this equation. Then k plus 1 is replaced by k. So I get the k and r minus k plus 1, which are the Euler numbers of fibers of Q1 Q2. So this is a relation between the geometry and representation theory. So somehow the Euler number is very weak topological invariant of the space. But this passage from this correspondence, so this, as I said, this is not the correct correspondence. But nevertheless, if I compute this pull back and push forward or in this co-normal bundle construction, then miraculously we get Euler number of the fibers as a result. So this is somehow the good exercise for the intersection theory of the in this Poincare duality business. But I just don't go all the detail, but I just illustrate why this Euler number appears in this computation. So in general theory of the intersection theory of Poincare duality, we naturally get the Euler class of the normal bundle to submanifold. So Poincare duality, if you have a submanifold, then it gives a homology class. And by Poincare duality, you should consider it as a cohomology class. So this is just given by the first you consider the Tom class of the normal bundle and then extend. So anyway, so you get the Euler class of the normal bundle. But so in this case, somehow by this construction, you replace normal bundle by the cotangent bundle by the following reason. So I just linearize and considering instead of submanifold, I consider the subspace in the linear symplectic vector space. So this conormal construction gives a Lagrangian subspace, as I briefly mentioned. So then it is well known that the symplectic vector space, if you have a Lagrangian subspace in the symplectic vector space, then this M is naturally identified with this Lagrangian subspace and its dual subspace. So if you know about this quantum mechanics, then L star is the moment direction, right? So this natural pairing for the symplectic vector space is identified as natural pairing between Lagrangian subspace and its dual subspace. So if you consider the normal bundle of this submanifold, it means that I consider the quotient, if I linearize, I consider the quotient space of M by L. Then this is the M divided by L, but by the reason what just explained, M divided by L is identified with L star. So this is a dual to L. And if you go back to the nonlinear situation, it means the normal bundle to a Lagrangian submanifold is a dual to the tangent bundle. And then tangent bundle, Euler class of tangent bundle is closely related to Euler number. And finally, this sign, strange sign in this result, R minus K and K minus 1. In fact, these are dimensions of fibers. And this appears because the Euler class of the dual bundle is just given by the Euler class of the original bundle up to the sign, and this sign is minus 1 to the power rank E. for the complex vector bundle. So this is the essential point of the argument to compute these coefficients r minus k plus 1 and k in geometry. Okay. So in this way, by little bit of the intersection theory, you recover this result in this. In some sense, the proof is not so difficult. So this is a relatively elementary calculation in intersection theory. And as I said, the construction is also somehow natural. But I think the non-trivial part of this theorem is to find that this kind of result holds, right? A priori, there is no relation between the representations of SL2 and the Grassmannians. So although this is very natural, but still it remains a mystery that why you have some connection between this cotangent bundle for Grassmannian and this representation. And for the Quiver varieties, it has some similar flavors. Quiver varieties, of course, naturally defined from starting from Quiver or Dinkin diagram, if I put the orientation. But I mean, there's no a priori correspondent relation except this combinatorial fact that this Katsumudi algebra is classified by stinking diagram. There is no conceptual relation between the Quiver varieties and Katsumudi algebras. But somehow by this experimental construction of this kind of given by correspondence, we can realize that the representation of Katsumudi in a similar way. Yes, the conormal bundle construction can be generalized to the case of Quiver varieties in a straightforward manner. So I introduce intermediate space PIVW for each choice of vertex I. So I take V prime and VW are the common, and I change V by V prime at the vertex only I. So V prime is one dimension smaller than V. And I have a map P1 and P2 as in the conormal bundle case. And this intermediate space is a closed loop. So BAB is as usual as for the Quiver varieties. And I also take the codimension one subspace in VIs such that the maps into VI factored through this subspace S. So this is a condition. So I have AIs and BH from WIs and VJs. And this linear maps a priori goes to VI, vector space VI. But I impose that these linear maps factors through the subspaces. Then I have I can restrict the map from VI to other vertices into S. Then the momentum equation is still satisfied. So I have a map from EI to MV prime down. And for the second, I can just forget this subspace and then get this MV down. And you can show that this PI VW is a Lagrangian submanifold in the product of MV prime W times MV W, as in the case of the conormal bundle. And you can also study what is the fibers of these maps P1 and P2. And fibers are again the Grassmannian manifolds. So in the previous example, it was a projective space, but in this case, this is Grassmannian. Now I prepare the main theorem. So first of all, I need to define the operators correspond to Cartan subalgebra. This is just the easy part. So I just assign the weights to V and W in the following way. So for W's, I consider the lambda, weight lambda, dominant weight lambda given by this formula. This large lambda I is the I's fundamental weight. And this mu is given by V by this formula, lambda minus sum over dimension Vi times alpha I. So lambda I is the fundamental given by this. Alpha I is simple. So starting from W and V, I define the weight, two weights, right? This is highest, lambda is highest weight, and this mu is weight in the example of the cotangent band. And it will be so also in the case of more general quiver varieties. Then this is the main result. I again consider the pullback and push forward, and I multiply appropriate sign and take a sum over all dimension vector p's. So this is the dimension, my definition of EI, and similar for Fi, I just replace P1 and P2. And the main result says this defines the representation of Kac-Moody real algebra on the top degree homology group of M beta. And each sum, to the direct sum of the all homology group. And if I take the summand, this is a weight space, and this weight is mu, as I mentioned already. And in fact, this is also irreducible representation, and also by general theory of Kac-Moody real algebra. So this it just means that this is. Oh, maybe I also said this is by concept. It's not so difficult to show that this is integrable. So once you have integrable representation, irreducible means highest weight. So this is integrable highest weight representation. This operators EI and Fi together with H gives the integrable representation, integrable highest weight representation V lambda. And that this is classified by dominant weight, and this dominant weight is lambda, which is given by this dimension of this vector space W. And the highest weight vector is the case when V is equal to 0, maybe equal to this formula. So if this is mu is equal to lambda, it means that this Vi is equal to 0. But if Vi's are all 0, then this quiver variety is just a point because there's no linear map at all. And by the homotopy equivalence between the MVW and the Lagrangian subvariety LVW. So this top degree homology, or maybe I should say, this is not top in MVW. This is the middle degree in MVW and the top degree in the Lagrangian sense. So this is isomorphic. And moreover, because this is a top degree, so LVW has several irreducible components of these dimensions, and you have a natural basis of this vector space given by reducible component of LVW. So in the second examples of two P1s, two unions of cotangent bound P1s, I have two P1s, union of two P1s as a LVW. So in this case, fundamental class of each P1, so you have two fundamental classes. So this gives a basis of two-dimensional space. So I get to two-dimensional space in that case. Oh, this is and in this example, by computing highest weight, this is 1 and 1. So this is nothing but adjoint representation by 3. And when both are one dimension, so the weight mu is equal to 0 if you go back to the formula in the previous page. So this is a weight 0 space in the adjoint representation. This is a Cartan subalgebra of SL3. And this is two-dimensional. I mean, SL3 is 3x3 matrix, trace-free 3x3 matrices. And if you, this Cartan subalgebra is a diagonal matrices, so you have two-dimensional space. And this two-dimensional space are spanned by those two P1s. So in this case, at least the dimensions, it is very easy to check dimensions matches. Okay, the proof of this theorem is again not so difficult, not so difficult from the sketch of the proof of Ginzburg's theorem, which I briefly explained. The most difficult part is the proof of the this relation, checking of this relation, commutator of E and Fy is equal to H. But in some sense, I pick up a particular vector, a particular vertex I, and I can look at I can focus on the linear maps related to vertex I. So remember that in the second example, this example. So I have the two open subsets B1 non-zero and B2 non-zero, and each vertex I see the quiver variety for the single vertex. So this is a mechanism why by imposing this kind of condition, I can somehow focus on a single vertex. So this is a general feature in the quiver vertex. Quiver is could be very complicated. You may have various vertices, many vertices. But if I pick up a particular vertex I, then I can forget most of other vertices for this kind of computation. So the quiver is a combinatorially complicated object, but somehow miraculously for this kind of computation, I can focus on the particular vertex and just to look at the linear maps related to vertex I. And similarly, for Katsbudi algebra is given by generator and the relations, and the generator corresponds to vertex I. By those two relations, somehow you don't need to consider the arbitrary quiver. Somehow, for the computation of these coefficients, you just look at the linear maps around I. So this is a essential point of the proof of the defining relation. Sorry. So I first check those operators satisfy the defining relations, and then I in the second step. So maybe secretly this result a combination of two statements. One is this gives a satisfy the defining relation of the Katsbudi as well. But the second statement is the integrable highest weight property, and this guarantees the irreducibility. So the highest weight property is important. So you must check that. So fortunately, as I mentioned, so I have a natural basis of this homology group. So somehow I need to understand the irreducible component of this Lagrangian subvariety. And for the proof of highest weight property, so we use inductive construction, irreducible component of this Lagrangian subvariety. So I have P1, two P1s in the second example, and those two P1s can be somehow inductively understood from the lower dimensional space. So I don't have time to explain the detail of this inductive structures, but this is very important, in fact. So this gives Kashiwara's crystal structure on the set of irreducible components. This is a combinatorial skeleton of the representation theory, which is originally introduced in the study of the crystal basis of the representation of quantum enveloping algebra. But anyway, so you have some combinatorial skeleton of this crystal structure, and this abstract combinatorial object, and this irreducible component as the structure of crystal. maybe I don't have time to discuss the further topic. Maybe just I just mentioned that there are some additional topic which I plan to talk, but unfortunately I don't have time. So the first topic I planned to mention is the case when we allow edge loop. And in this case, you have the Heisenberg algebra instead of Katsumudi algebra. And in the second and third part, I plan to talk about the tensor product realization of tensor product representation. And that is somehow very crucial for the later development of the Quiver varieties. So this main theorem just gives the realization of the irreducible representations. But if you take the two copies of irreducible representation and consider its tensor product, then it's natural to ask how you can realize this tensor product. And then geometric realization. So if you are interested, so I just put this presentation file in the chat, so you can look at this file. Okay, thank you very much for your attention. So I stop this.